What notes did I just play? Actually, you don't need any musical talent to answer me. All we need is a Fourier transform, a mathematical tool that decomposes an input into its components. Each note I played has a distinct number of vibrations per time, or its frequency. When I played different notes together, I added up their waves. Some parts will cancel out, while other parts will become amplified. Adding more waves will only make the total wave more complex, but this is what a microphone or our ears hear. It's the Fourier transform's job to decompose it into the original waves of different frequencies. So how does it do that? Let's look at pure A4 natural. It has a frequency of 440 Hz, meaning it goes through a peak or valley every 4/40th of a second. If we take this graph and wind it, we get a fairly center shape all around. Until we wind it so that all the peaks overlap with peaks, valleys with valleys, and so on. This is where our winding frequency equals A4 natural's frequency. The magnitude of how off the graph is from the origin shows the intensity of this winding frequency in the pure A4 natural. And of course, this magnitude for other winding frequencies should be very small for anything other than the frequency of pure A4 natural. And shifting the graph only rotates the winding. The magnitude is the same. The graph we drew, scaled by the amount of sample, corresponds to the Fourier transform of A4 natural, which shows intensity over frequency, not over time. Similarly, the Fourier transform of other single notes should have single peaks at their frequencies, and by winding their combination, we get a neat Fourier transform that shows all of those frequencies. Now, if we wanted to take away any of these notes, we could eliminate a frequency and combine them, giving a different total wave.
That's how audio editors identify
and remove background noises. But the Fourier transform can be used to decompose shapes too, like this leaf. As I trace the outside of this leaf as time passes, I plot the x and y positions. This produces two waves, for x and for y, which we can use the Fourier transform on. And since the wave shows x and y positions along a circle, each of these waves shows motions along different circles, adding up to trace a shape. With this technique, we can approximate any path with circles or, really, waves. So the central idea here is that any seemingly random data given over time, like sound, position, electrical signals, and even stock prices, are made of simple waves of different frequencies. The Fourier transform, in the end, embodies the spirit of math and science, to find hidden order in disarrangement.